ID the Future, a podcast about evolution and intelligent design.
Welcome to ID the Future. I'm Eric Anderson, and we're here live in Denton, Texas for the Conference on Engineering and Living Systems. I'm sitting down today with Casey Luskin, Associate Director of Discovery Institute Center for Science and Culture. Casey is a lawyer and also has a PhD in geology, so an interesting mix, and I know you've done biology studies as well, Casey. Casey was a presenter at our conference, and we'd like to talk to him a little bit about his work today. Welcome, Casey.
Great to be on with you, Eric.
So, Casey, you talked a little bit about three models in the fossil record. What are those three models that you're sharing?
Yeah, so my talk was titled Patterns from the History of Life, Abrupt Appearance, and Stasis. And the first part of the talk basically looked at various models of how we understand and interpret the fossil record. And of course, the first model is the most famous one that everybody has seen in textbooks or PBS NOVA documentaries. It's the gradual Darwinian model, descent with modification model of the fossil record, where basically you have organisms very gradually changing over time from one form into another. Species morph very slowly. You have sort of these species that will very, very slowly over long periods of time through many intermediate stages, many transitional forms and phases will morph from one body plan into another. And of course, if this model is true, then it's supposed to leave lots of transitional forms because the change happens slowly, plenty of time to fossilize many of these intermediate stages between various types of organisms in various morphological states. So that's the classical Darwinian view of the fossil record. But of course, as the story goes, Darwin predicted that we should find these transitional forms. He was aware of the lack of transitional forms in his day. He said it's just that the fossil record is incomplete or that our knowledge is incomplete. And so everyone expected that as they studied paleontology and looked for more fossils, then these transitional forms would be discovered. Well, then about 100 or so years after Darwin, folks began to come to terms with the fact that, you know what, we've been searching for these transitional forms for a long time. Yeah, there are a few possible candidates here and there, but by and large, we have not found these predicted transitional forms that we ought to find if this Darwinian gradualistic model of the fossil record is true. So this brings us to the second model of the fossil record, which was really conceived in response to this recognition that we're lacking Darwin's transitional forms. And this is the punctuated equilibrium model of the fossil record. And under this model, yes, you still have universal common ancestry between organisms. Yes, you still have natural selection as the driving force that is sort of driving evolution. But the difference here is that the change, the speciation takes place in very short periods of time in very small populations, such that there is not very many opportunities for the transitional forms to actually get fossilized because very few of them actually live. The easiest way to get a new species is to sort of have this allopatric model of speciation where a subpopulation of some species gets isolated from the parent population and then it undergoes maybe, there just happens to be, due to the law of averages in the small population, maybe a weird gene pool, and then there's some selection pressures and this small population suddenly changes its morphology. And this happens quickly. It happens in a small population. Again, there's not a lot of time for transitional forms to be fossilized. And lo and behold, out pops a new species, okay? And according to this model, this happens over and over again. You get new species appearing, new body types, fundamental new types of organisms appearing without transitional forms. Then there's, of course, a model that I call the data, or what you might call the more explosion-based model of the fossil record. And this is really based upon the recognition that when you look at the fossil record, what you see is a repeated pattern of explosions of new types of organisms without evolutionary precursors and without transitional forms. One of the objections that has come up to the punctuated equilibrium model is that, well, look, you're telling us that all this evolution took place, you're saying that it happened, but you're saying that you can give us no evidence from the fossil record that actually confirms that these transitions took place. It's always inferred based upon sort of a lack of evidence. It's almost like the punctuated equilibrium model predicts that you will find no confirming evidence. Well, that does not make for a very persuasive theory. And so what I think that the explosion model, or what I would call the data model, does is it just lets us take the data of the fossil record at face value. It's showing us repeated patterns of major groups of organisms without these transitional forms, without evolutionary precursors, and we don't have to infer something that we're not seeing. We don't have to infer evolution that's always hidden or not really there. We can just take the data at face value and say, okay, well, this type of organism, this group appeared abruptly, and that's what the data is telling us, and we're just going to kind of leave it at that. So I guess that would be the dominant pattern in the fossil record. It's not Darwinian gradualism. It's not punctual equilibrium. It would be this explosive appearance. We see this over and over again throughout the fossil record. And I'm not saying that there's no possible examples of transitional forms. Yeah, I mean, that does happen sometimes, but the dominant pattern is this pattern of explosion.
Yeah. The reason why we don't see all these transitionals is because we got bad data, right? What we know is the artifact hypothesis. And then Gould and Eldridge come along and they propose, I've always been a little bit amused by punctuated equilibrium because it seemed to be a theory based on a lack of data. And like you say, it's kind of funny because, well, where do we go to find this evolution? Well, you can't find it. That's just what we predicted. You won't find the evidence, So it's kind of a funny way to approach it that way. Yeah, so tell us a little bit more about the data with respect to, say, something like the Cambrian explosion.
Sure, and eventually biologists couldn't keep saying, oh, it's imperfect, this is an artifact. In fact, my evolutionary biology 101 professor during my undergraduate studies, he was David Woodruff. He passed away a number of years ago. He was a very good professor, though. He had a paper in the journal Science published, I think, in 1980, where he said evolutionary biologists can no longer ignore the fossil record on the grounds that it is imperfect. And I believe that he did his PhD under Gould. So he was definitely a student of Gould, and he was thinking in terms of, look, we can't keep just explaining away the lack of transitional forms by saying the fossil record isn't perfect or we just need to do more research, more digging in the ground. We have to come to terms with what this is a pattern that's real. We have to be able to explain it. And I respect him a lot for saying things like that. So yeah, getting into this world of explosions, certainly the Cambrian explosion is the most well-known explosion in the fossil record. It's when most of the major animal phyla, the major groups of animals called the phyla, appear in the fossil record in basically a geologically short period of time. We might say it's 5 to 10 million years during the Cambrian period that many of these animal phyla appear. We're talking about organisms as diverse as arthropods, brachiopods, chordates, echinoderms, maybe even mollusks and others as well, ctenophores, very diverse body plans that appear in the fossil record abruptly, and they appear without any evolutionary precursors. In fact, Richard Dawkins said it is as though they, speaking of the Cambrian fossils, were just planted there without any evolutionary history. Or there's an invertebrate biology textbook which says that most of the animal phyla that are represented in the fossil record first appear fully formed in the Cambrian some 550 million years ago. The fossil record is therefore of no help with respect to the origin and early diversification of the animal phyla. This is really an incredible observation that we sort of kick off the fossil record of animal life with this abrupt appearance of all these diverse groups, and there are no apparent evolutionary precursors. So it's a problem for Darwinian evolution, but as we tried to do here at the Conference on Engineering in Living Systems, we're not just trying to boo Darwin, as we're saying, we're trying to understand these patterns from a design perspective. What does that mean? We can get into that, but yeah.
Yeah, I know that some folks are still doubling down and saying that even the Cambrian explosion is just an artifact of an incomplete fossil record. How would you respond to those kinds of?
Yeah, if you listen to popular evolution defenders, there's still a lot of sort of pop evolution apologetics arguments out there that will say, oh, the Cambrian explosion is not real. It's just an artifact of an imperfect fossil record. The result of us not having the appearance of hard parts like shells or bones or exoskeletons until the Cambrian period. It's saying that it really didn't happen. It's just, once again, the fossil record is incomplete and our eyes are deceiving us. We've got bad data. Well, there's a number of artifact hypothesis arguments. One is that we really did not have rocks in the earlier pre-Cambrian periods that were good at preserving fossils. But that's really not true because we do have fossils from earlier periods. We do have pre-Cambrian fossils. I talked about this in this talk. We have the Ediacaran fauna, the Vendian fauna, which is another explosion in and of itself, where you get these weird sort of colonial organism, algae-like type things. We're not sure exactly what they are, but they appear abruptly and then they disappear, but they were preserved. Okay, so we do have rocks in the Precambrian leading up to the Cambrian period that could preserve fossils, and organisms if they were there to be preserved. But we don't see ancestors to the Cambrian organisms. And another point is that many of these Ediacaran fossils, they're soft-bodied. In fact, I think it's safe to say that they're all soft-bodied. So it's not the case that the Cambrian explosion just represents the evolution of hard parts, which suddenly could allow for fossils to start being preserved. No, we see soft-bodied fossils in the Precambrian, and by the way, we see lots of diverse soft-bodied organisms appearing in the Cambrian as well, which is really interesting. So the reality is when you consult sort of experts on the Cambrian explosion, people like Douglas Irwin and James Valentine, in their 2013 book, The Cambrian Explosion, they go through this artifact argument and they settle on this. They say several lines of evidence are consistent with the reality of the Cambrian explosion. Or if you consult a Dutch biologist named Martin Scheffer, he says, it is now generally accepted that the Cambrian explosion was real. This is in a Princeton University Press book from 2009. So when you consult, expert paleontologists and not sort of YouTube apologists, they see, okay, we can take the artifact hypothesis a little bit, but it does not go very far to explain the Cambrian explosion. It was a real event.
So are there some other examples that point to this explosive fossil record?
Yeah, there are lots of other examples. And let me say that if you want to learn more about this, the number one document to consult is a chapter by Gunter Beckley and Stephen Meyer in the book Theistic Evolution. It's a fantastic chapter where they go through these explosions throughout the history of life, and they document it all to the mainstream peer-reviewed scientific literature. So after the Cambrian explosion, we have something called the Great Ordovician Biodiversification Event. It took place probably between 485 to 443 million years ago, and we see in this period a rapid increase in the diversity of various marine invertebrates, things like brachiopods, gastropod mollusks, bivalve mollusks, and others as well. And this marine invertebrate explosion takes place at the level below the phyla. It might be orders or classes or families and so forth of various marine invertebrates, but there's an explosion that takes place there, and it's well attested in the fossil record. And then after that, we have the Devonian nekton revolution. Organisms with the nekton would basically be swimming organisms in marine context. And we see an explosion of various types of jawed fish or ammonoids, these cephalopods that are very popular fossils in the fossil record. And this is recognized as another explosive diversification in the fossil record. In fact, Arthur Strahler, who was sort of a skeptic that wrote a book in the 80s where he said that the origin of major groups of fish can only evoke in unison from paleontologists a plea of nolo contendere, which of course means no contest in response to the critics. Then in the Silurian and the Devonian, we see a terrestrial plant explosion, and it's also been called the Devonian explosion of plants, and it's also well attested. It's been compared to sort of the plant equivalent of the Cambrian explosion, and so very interesting that we see this explosion of plants in the fossil record. Later on, we see what's been called the big bloom in the fossil record, or the explosion of angiosperms, flowering plants. Darwin was aware of this. He called this an abominable mystery, which did not fit well with his theory, but it's still around today. In fact, a paper in Trends in Ecology and Evolution said angiosperms appear rather suddenly in the fossil record with no obvious ancestors for a period of 80 to 90 million years before their appearance. And so this is still a big mystery for a Darwinian explanation. When we get into some of our familiar groups of vertebrates, a bird explosion has been cited in the late Cretaceous. We see the explosive evolution of major living bird groups. And then there's a mammal explosion in the early Tertiary where many orders of mammals, major groups of mammals, appear abruptly without sort of these transitional intermediate forms. And then, of course, when we get to the appearance of our own species, or I should say our own genus, Homo, the first human-like members of the genus Homo. We're talking about things like Homo erectus. They appear abruptly, and this has been well attested in the fossil record. In fact, there was one commentator from the University of Michigan that called it a Big Bang theory of human evolution because of this abrupt appearance of our genus Homo in the fossil record. And I've talked a lot about this in the past. It's very well attested to in the mainstream scientific literature. We could go on and on about this. Read the chapter by Beckley and Meyer in the book Theistic Evolution. You'll get even more examples that we've talked about here. But again, this pattern of explosion is the dominant pattern that we see in the fossil record.
Now, the other side of the coin is what we call stasis. Tell us a little bit about that.
Yeah, before we say, look, if you're skeptical of this, consider this quote. This is from Ernst Mayr, one of the architects of the modern synthesis, okay, one of the most famous biologists of the 20th century. He lived into the 21st century as well. In a 2001 book, so, not that old, he said that new species usually appear in the fossil record suddenly, not connected with their ancestors by a series of intermediates. So, this is not just coming from ID people. This is coming from very mainstream people, Harvard biologists like Ernst Mayr and others as well. I could cite all kinds of quotes. I want to get on with this conversation, but this is well attested. So what is stasis? So stasis is basically exactly what you might think it is, where in the fossil record, after we have these explosions of new types of organisms, these body plans remain largely unchanged for long periods of time. And so this is another observation that evolutionary paleontologists have had to grapple with. Why is it that we see not only this abrupt appearance, but we see this stasis? Stephen Jay Gould really tried to get his field to come to terms with the reality of stasis. He wrote in a paper in the year 1991, he said, stasis is data. We can't just ignore this. We may not be seeing change, but that doesn't mean it's not interesting. We have to understand why are these species not changing. In another article in Natural History, he said, stasis or non-change of most fossil species during their lengthy geological lifespans was tacitly acknowledged by all paleontologists, but almost never studied explicitly because the prevailing theory treated stasis as uninteresting, non-evidence for non-evolution. The overwhelming prevalence of stasis became an embarrassing feature of the fossil record, best left ignored as a manifestation of nothing, that is non-evolution. So the question for us ID theorists, what do we mean? What is happening when we see stasis? Why do we see, for long periods of time, these body plans are remaining stable? I want to also go back to that book, The Cambrian Explosion, is its title, by Doug Irwin and James Valentine, two leading Cambrian explosion experts. They asked this question in their book: why have these morphological boundaries, talking about the body plans in the Cambrian explosion, why have the morphological boundaries of these body plans remained relatively stable over the past 500 million years? That's stasis. They want to know why all these body plans that appear abruptly in the Cambrian explosion haven't changed. It's very interesting, and it really is a vexing thing for someone who's defending a model that says that life has changed so much over time.
I really like Gould's point. When you see an organism not changing for millions of years, that's data. You don't just ignore that and say, well, nothing interesting is happening because it's not turning into some other different organism. That's right, because it didn't turn into another organism. It's stasis. So that's an important point that you're bringing out there.
Well, Eric, this fits really nicely with your sort of engineering, I don't know, what do you want to call the model of adaptation that you presented in another podcast?
The bounded adaptation.
Bounded adaptation, yeah.
Right, exactly, because we were talking about the fact that organisms, yes, can adapt to their environments, but they always do so within boundaries. And they're still, the peppered moths are still the moths, the finches are still the finches, the E. coli are still E. coli. And that's very consistent with the engineering model. It's also consistent with what we see when we look at orphan genes or taxonomically restricted genes like Paul Nelson has talked about. It's consistent with what we know from information theory. So all these different avenues of evidence, I would say, are converging on the idea that once you have a functional form, it's going to remain essentially, if we use the term from geology now, or paleontology, in stasis largely until it goes away. It comes fully formed and it remains in that stasis.
And we're getting ahead of ourselves in the conversation here, but I think what you're saying needs to be said. This is an ID-based model that can explain abrupt appearance and stasis. We can talk about that some more, but I think that it's really important. And what you have done is sort of outlined these organisms are designed to change, but they're designed to change within limits. They're not designed to change as something fundamentally different, some other isolated gravity well, as you put it. They're designed to change within limits, and that's why we see stasis.
Right. So You want to cite a couple of particular examples in that fossil record of stasis that are particularly interesting?
Sure. I mean, there's lots of examples. When you go through the fossil record, I mean, you go to a fossil store and you can see things that you immediately recognize, right? You can see a gastropod, a snail, and you're like, oh, wow, that looks like something that I could have found in the garden or found at the beach, and the shape of the shell is very similar. So snails, gastropods trace back tens of millions of years, probably at least 100 million years. Preapulid worms. I had the pleasure, the fortune to go to the Burgess Shale fossils back in 2012. And while there, they let you just sort of play around, dig through the fossils, and take photos. Of course, you can't take them with you, but you can take as many photos as you like. So I took pictures of them, and then I brought them home, and I looked at a species there called Atoya prolifica, which is basically a preapulid worm, and compare that to a living preapulid worm, and you could see that a living worm could leave a fossil impression just like the ones that you see in the Cambrian. And so it's remarkable, hundreds of millions of years, back 500 million years, and it's almost the same. Horseshoe crabs, this is a very famous example of stasis. They go back at least 400 million years, perhaps up to 440 million years, and the fossils of horseshoe crabs look almost identical to living horseshoe crabs that are around today. The tadpole shrimp goes back about 360 million years. And look at a picture of a tadpole shrimp compared to a fossil, and they're almost identical. Bivalve clams, mollusks, go back some 500 million years. Brachiopod, lampshell brachiopods look almost identical in the fossil record to the way they look today, probably going back some 500 million years. Let's see, the coelacanth is a great example, a very interesting example, because for many of these, we first had the living specimen, and then, of course, we're finding fossils going further and further back that look essentially the same as the living specimen. Mm-hmm. But with the coelacanth, we had the fossil example first. I've seen different suggestions. It might be 70 million years or perhaps up to 200 million years, the coelacanth fossils. But we have these fossils that go back many tens of millions of years. And then in the 1930s, they discovered a living coelacanth. And at first, nobody believed that they'd actually found this living coelacanth because they thought it had been dead for many millions of years. It was found off the coast of South Africa. It's a really fascinating story. These biologists, they had no clue at first that this was actually a coelacanth, and then they realized, oh my gosh, what we have is a living fossil, when some experts took a look at it. So it's really quite amazing. Sharks go back perhaps up to 400 million years. You look at a fossil shark and it looks like a shark. Well, you would recognize as a shark today. And crocodiles, 200 million years going back in the fossil record. And it's not just animals, but also plants. Ferns go back in the fossil record some 180 million years. The ginkgo is a plant that you can see around today. It goes back over 100 million years. Cycads are also very ancient. They go back to the Jurassic. We can recognize cycad plants. And there are pine trees in Australia, the Wollemi pine, that is known from fossils going back 50 million years. The nightcap oak goes back, I believe that's from New Zealand, goes back some 90 million years in the fossil record. But perhaps the best example of all are stromatolites. Stromatolites, of course, are these bacterial mats. I had a lot of opportunities to see stromatolites in the field when I was doing my PhD work. Some of the rocks I studied actually had stromatolites in them. I didn't touch them. I left them there. I don't want to do geo-vandalism, as we call it, but I took some nice photos of them. These were 2.95 billion year old stromatolites that I studied, or were in the rocks I was studying for my PhD thesis. But, they go back perhaps even as far back as 3.4, 3.5, even 3.7 billion years. It's been suggested that we have evidence of stromatolites in the fossil record. Well, there are living stromatolites that are still alive today in Shark Bay, Australia. And I've also seen suggestions that there might be a location in Baja California where they exist, and others as well. So stromatolites have basically been around since the beginning of life, these bacterial mats. So it's a great example of a living fossil. There's still stromatolites. They look pretty much the same, yeah.
Okay, we've talked about the explosions, we've talked about the stasis. Is there an ID-based model that works better, in your opinion, than the attempt to punctuate equilibrium or Darwin's original attempt?
Yeah, so I think that there have been some great insights from Steve Laufman and Howard Glicksman, who published the book Your Designed Body last year in 2022, and they talked about what does it take to create a functional system. And I want to read a couple quotes from their book, because I think these quotes naturally lead us into a sort of an understanding of why organisms have to appear abruptly in the fossil record. So here's a quote. They say, given the amount of work required, decisions plus actions to create them, talking about coherent systems, they say coherent systems are nearly always made through relatively large, discrete jumps in functionality. The greater the number of coherent, interdependent parts or subsystems, the more work it takes to change a working system into a different working system. They go on to say, because more complex body plans have more parts, more orchestrations, more interdependencies, they are more resistant to change, meaning changes can occur only at much higher cost and at much less often with much simpler body plans. Regardless of the causal force or action, we therefore expect changes in the most complex body plans to be few, infrequent, and relatively minor over time. Because of this, we're not surprised that the fossil record contains no intermediate forms between distinct animal body plans or phyla. So basically what they're saying, Eric, is that complex systems appear as functional interdependent wholes. If you don't have the whole system there, it's not going to work. So it makes sense in the fossil record that if you're going to get a completely new type of organism with a new body plan, a new body architecture, maybe a whole new way of making a living, a new niche that it lives in, a new system essentially is appearing, it's going to appear abruptly and fully formed. So no wonder when we look at, quotes from mainstream science, we see things like this. This is a quote from a zoology textbook. It says, many species remain virtually unchanged for millions of years, then suddenly disappear to be replaced by a quite different but related form. Moreover, most major groups of animals appear abruptly in the fossil record, fully formed, and with no transitionals yet discovered that form a transition from their parent group. So I think that an ID-based model, when we understand that the complexity of organisms requires them to appear abruptly, requires a massive sort of immediate infusion of large amounts of information into the fossil record to generate this fully formed system, the only way you're going to be able to generate all the information needed to yield an organism that's alive and functional all at once is through an intelligent cause. And then you have sort of an ID-based model that you've outlined really nicely, Eric, that can explain why these organisms don't change radically in terms of their body plan over their long subsequent histories. So we can account for both the abrupt appearance and the stasis in the fossil record through an ID-based model. I know you've done thinking about this as well. So any thoughts from you, Eric?
Yeah, just as we mentioned, whether we're looking at what we see in the lab with E. coli, whether we're looking at the genetic evidence in terms of orphan genes, whether we're looking at information theory and how that relates, all of these lines of evidence are just really pointing to the same thing, which is, yes, if you're going to get an organism to function in the real world, in real time, in three-dimensional space with real materials, that's a hard problem. And it has to be coherent, it has to be functional, it has to have everything together. And then changing that, as Laufman and Glicksman noted, into something completely different is just not something that happens by happenstance. And so you're going to have this stasis that you see once something comes along and is functional. So multiple lines of evidence, I think, are just really confirming what you're saying, Casey.
What's really exciting, I'm sure a lot of folks here at the conference feel the same way, is there is a theory of biological design that is slowly emerging here. I'm sure it's got a long ways to go, but it's already able to explain a lot of data that frankly is challenging to an evolutionary paradigm. And it's very important data. I look forward to seeing where all this goes in the future.
Well, Casey, thank you so much for being with us today and helping us understand more about the fossil record and how an intelligent design perspective can actually make better sense of the data than we get from the traditional models. So appreciate you being with us.
Yeah, thanks, Eric. It's been a lot of fun.
For ID the Future, I'm Eric Anderson. Thanks for listening.
Visit us at idthefuture.com and intelligentdesign.org. This program is copyright Discovery Institute and recorded by its Center for Science and Culture.